First, let's start with what you spoke about, the probability cloud for electrons, and they're not a fixed orbit. Such a lie that I was taught in high school. This is the perfect point to introduce quantum physics. What is quantum physics?
So quantum physics is the most successful theory in the history of human thought. That's what it really is. I think there's no doubt in my mind that that statement is true. And I don't think it's emphasized enough. It's incredibly successful because it explains phenomena all the way from what we were just discussing, electrons around protons, to the source of energy of the sun, which prior to quantum mechanics was a big mystery, to nuclear power and nuclear weapons, to the origin of structure in the universe. Where did galaxies come from in the first place? To the fact that if you take a cheap fluorescent light, it makes you look a little bit ill. And if you send that light through a diffraction grating or just take a CD or a DVD and reflect the light off it, you'll see that it's not a perfect rainbow. It's got only certain colors in it. So that's because the molecules in the gas are emitting only certain frequencies of light. All these things are consequences of quantum mechanics. And as you can see, they're on completely different scales and completely different regimes of the physical world. But they're extremely easy to understand and explain and make very precise predictions about with quantum mechanics. So it's very, very successful.
Let's define some of the terms in quantum physics.
Sure, yeah.
What is the wave function? What is entanglement? What is the uncertainty principle?
Okay, all right. Well, let's start with quantum. So quantum means discrete in the sense of not continuous, right? So, and it's called that because many quantities, not all, but many quantities in quantum mechanics are discrete. So one of them are, one such example, it would be the set of energies allowed for an electron that's bound to a proton. So in a hydrogen atom, the electron can't have any energy it wants. It has to have a certain discrete set of energies, at least up to some point. If you give it enough energy, it'll ionize. It'll become disassociated from the proton and fly off freely. At that point, its energy isn't quantized. But if it's going to be bound to the proton, certain energies are allowed. So that's the quantum in quantum mechanics. It's important to say not everything is quantized, even in quantum mechanics. For instance, the energy of the electron after it's ionized, not quantized. It can have any energy. Okay. So that's quantum. Now, what is the wave function? The wave function is the description of the state of the system you're talking about. So it's called a wave function because in quantum mechanics, there are phenomena that look a lot like interference of waves. And mathematically, it is a sort of a wave. And when you add together two waves, physically, if you shine light along two paths and then bring them back together, you'll see an interference pattern. Or if you think of waves on a beach, if there's a rock or something, or a wall with some openings in it, waves will come out of those openings or around the rock, run into each other, and you'll see a kind of a pattern of waves crossing each other. That's an interference pattern. So it's called a wave function because quantum mechanical states behave in that way. They interfere. Interference. Now, what else did you ask?
Entanglement and uncertainty.
Yes, thank you. All right. So entanglement is a tricky concept, but an absolutely fascinating one. I would start in the following way. So imagine that you have a green ball and a red ball. You have two friends, Alice and Bob, and you tell Alice and Bob that you're going to mail each of them one of these two balls. And the way you're going to do that is you're going to flip a coin. If you get heads, you send Alice the red ball, and if you get tails, you send her the other ball. Okay, so now you package it. You do this. You flip the coin. You package up the balls. You send them off. And Alice and Bob live very, very far apart. One at the South Pole, one at the North Pole. They don't have any internet. They have to communicate by carrier pigeon, which takes weeks. Okay, but as soon as Alice opens her box and sees that she has the red ball, she knows what color Bob has, even though there's been no time for her to talk to Bob. So that's an example of gaining information about something very far away instantaneously. And there's nothing weird about it. It's the fact that she was able to gain that information is related to the fact that she knew what the setup was. She knew that you were going to do this and that you did that in the past. So instantaneous transfer of information sounds odd, especially to a physicist, because Einstein taught us that information cannot propagate faster than light. But in this case, it didn't. The information really originated with you in the past when you told Alice and Bob what you were going to do. And so what happened is that Alice's state of knowledge collapsed down to one possibility. And in that possibility, she knew the color of the ball that Bob received. Okay, so that's a kind of entanglement. That's a kind of classical entanglement. It's when two states, in this case, the colors of the balls, are correlated in such a way that information about one gives you information about the other.
Right.
What makes quantum mechanics different is that, well, In quantum mechanics, the state does not have to be a definite possibility. So a quantum mechanical state can include things like the probability cloud of an electron around a proton, where you don't know exactly where the electron is. You just know what its probability distribution is. And so entanglement between quantum states doesn't necessarily mean that you know definitively something about one and definitively something about the other. It does, however, mean that information about one gives you information about the other. So there's a correlation between the states. So that's more or less what quantum entanglement is. It's not that different from the classical version with the balls, but you have to add in the other aspects of quantum mechanics.